again, it's Cliff here on RapidTurn part 22, starting off this video looking into the strange surface finish issue that I was getting, and eventually ending up on a positive note doing a production run of accurate parts on RapidTurn with a good surface finish. Alrighty. I was going to do this job in RapidTurn, but until I get to the bottom of what's causing this really weird spiral pattern, seems to be 4 spirals within each other, until I get to the bottom of what's causing it, I'm really forced to do the job via spindle turning on my 1100. But it's quite an interesting job anyway, and shows you how suitable spindle turning is for this type of work. There's a total of 5 operations. There's a facing operation via this little tool here, and the final operation is so on one side, on the right hand side, there's a facing operation. You can see the scallop in the top rake there, and the final operation is cutting that radius on the entrance of the bore. And then it moves over to G55 for a center drill operation, G56 for a larger drill operation, and G57 for a deep drill operation. I'll just run it now and you can see it going through the stages. So if I stand back a bit, you might be able to hear me better. So that's the facing operation there. Let me come over to G55 center drill. Then across to G56 large drill. This is generating quite a bit of heat. We've got to be careful it doesn't grab the part. And finally, deep drill, form drill right deep inside the part. Sorry, not finally, that's operation 4. Finally, operation 5 is to come back and cut that entry radius on the form tool. When I was making these parts in aluminium, I had a real problem trying to get rid of the strange spiral surface finish, and it's 4 spirals at about a 6mm pitch, and so the adjacent spirals are about 1.5mm apart, and they're about half a thou deep. You can actually feel it with your fingernail, and it's quite pronounced. Anyway, I've been trying to get the same effect with this piece of test acetal, and it's pretty difficult to get it to do it today. Sod's law, I can't seem to find any setting that will bring it back to the same extent. You can just see it there, and I thought, oh, it's some sort of bearing vibration or oscillation or error in the spindle causing a vibration. So I deliberately tried to amplify the problem and put some weights on the chuck, and it's definitely vibrating more with that weight on it. But the surface finish is just the same. It's very faint though. It's really like the marks on a gramophone record, just a tiny little pattern this time, unlike the other day when I was doing an actual job. Then I couldn't get it to go away. Now I'm trying to expose it and I can't get it to show itself other than in this very, very faint form. So I think what I have to do is say that it's probably going to be a minor problem, give up on it for now and just keep using it, and if it comes back again, try and identify it then. It seems to vary strangely and disappear sometimes and come back other times, which should be a clue as to the cause of it. I've set up a piece of black acetal hoping that that would really show and do some test cuts with various settings to see if I can expose the problem, see if I can get it to show more clearly with some settings than other settings, and thereby expose the problem. But I'm not having much luck. It's very elusive. Just when you're trying to identify it, it starts to hide. Is that showing on the camera? I'll just review that. Here it's showing in a previous run of parts that I made. Okay, what I've done now is put in a piece of aluminium similar to the one that I had the problem with on the job, and I've set the parameters up the same. A feed per revolution of 0.05 or about 2 thou, and just repeated everything, and sure enough I'm getting that pattern back again. It's not very deep, but you can see there the spirals, and I'm starting to get a feeling for what's causing it. Okay, I'll take a cut now that's not controlled by the software and the encoder, but just a manual facing cut. Okay, let's have a close look. And you can see now that the spiral's not there, and that fits with my theory of what's causing the spiral, and I'll go into that now. So with lathe work, G95 and G96 are usually used, and they're used in the conversational programming. And G95 is a feed per revolution mode, and that is a certain depth of cut per revolution, in this case 5/100ths of a millimeter depth of cut per revolution, and G96 is constant surface speed and within boundaries, and in this case it's set at S300, that's 300 millimeters a minute, but with the boundaries of a maximum of 2000 RPM, and you can see those settings there. So what that means is when the job's running, the revolutions of the spindle are coordinated with the movement of the vertical slide, because the encoder on the spindle ensures that that occurs. So if you look at the surface finish of the two different methods of cutting, the inner surface is G95 and G96, a coordinated movement, a bit like thread cutting, and the outer surface is manually fed and it's not coordinated, and there's no problems with a pattern there. Now what I think's happening is it's actually not primarily due to G95 and G96, but G95 and G96 exposes a surface finish issue by presenting it in the form of a pattern, and manual feeding at a non-controlled coordinated rate doesn't expose it, because it doesn't form a pattern, it just forms a random microscopic surface finish. That's just a familiar faced finish. So if there's vibrations in the headstock, in the spindle, due to the motor, due to the bearings, or whatever, it records the pattern of the vibration on the surface, a bit like a old-fashioned vinyl record does. It has the pattern of the surface finish in a spiral form on the surface, and that's what I'm seeing. When it's a minor effect, as it is here, it's not really a problem. But if you happen to be getting a particular resonant frequency going at a certain RPM with a certain condition bearings or vibration in harmonics, it could become quite extreme, and that pattern presents itself because of the coordinated movement of the rotation of the spindle and the movement of the tool. It's not due to the tool retracting back across the surface on the return movement, because the tool is moving clear on both the conversational tool path and the manual tool path. So we know it's not that. It's not caused by the feed rate on the way down, because the feed rate is very much finer than the pitch of the spiral. So the only thing that's left really is that there's some kind of vibration or oscillation of the spindle that's causing a surface finish issue that is being recorded in the form of a spiral because of the controlled rate of rotations to feed rate. And in some cases, for example in this particular job, that vibration or oscillation is enough of an issue to give quite a pronounced corrugated effect. So it's identifying a issue in the headstock on this particular RapidTurn. It may be that there's an error in the bearings, or the fit of the bearings on the race, or an out of balance of the spindle or chuck or motor. It's causing a resonant vibration, but it is not primarily caused by the feeding process of G95, G96. It's just that they expose it in the form of a recorded pattern. The degree to which these grooves are a problem may also be due to the geometry of the tool. It may be due to the degree of the oscillation or vibration, but also due to the geometry of the tool. If the geometry of the tool allows the vibration to be cut in a defined way, perhaps with very steep clearance angles and a sharp cutting, a small radius on the cutting edge, it will be more pronounced. But if there's very shallow clearance angles and a large radius, more like a wiper tool, then the likelihood of it reproducing the vibrations in the surface finish would be much less. So perhaps a combination of the geometry of the tool and the oscillation, vibration, error in the spindle combined, under some circumstances, can give a really pronounced spiral such as this. My faith in RapidTurn is returning. I'm doing a run of parts now, quite a lot of parts that need to have good accuracy, a finishing cut and a settle. I'm just allowing it free to rotate in the chuck, bringing in the tailstock so I can just feel compression on rotation, then just nip it on the chuck so it's held very delicately so it doesn't distort. One finishing cut, and I'm getting really good consistency. I'm getting 13.83 down one end, 13.83 down the other. I'm easily within 1/100th of a millimeter each time. And that's partly because I better understand the thermal expansion. I'm controlling the RPM to a maximum of 1500. I'm avoiding long gaps in between part changes, and I'm adjusting for the difference in the height of the tailstock with a destination diameter and a starting diameter so that I can offset the taper really easily. So it's going 100%. So all of these tests have been really worthwhile, because although it seemed very tedious at the time, I've got a much better understanding of what's going on now and what are the parameters, and what I can do and what I can't do. And yeah, I'm really pleased with how it's going. You know, I was starting to wonder if I wouldn't have been better off buying a Slant Pro, but you know, by the time you count freight into the equation, you're talking $20,000 to have a Slant Pro with a turret tool change. And you know, you've got to include the cost of the turret, because otherwise you haven't got you've only got a 2-axis lathe. At least with RapidTurn, you've got a 3-axis lathe. You've got gang tooling, and once you can overcome some of the little idiosyncrasies of RapidTurn, it's very capable. Yeah, I'm getting really good consistent diameter now, and parallelness, and a really good surface finish. So my fears are fading away again. So just to reiterate, on a run of parts like this, if I keep the RPM to a maximum of 1500, it's really only warm. I'm not getting a great deal of thermal expansion. It's getting drawn away as fast as it's being produced, and I can adjust for the height and the taper in the code here. I've got a target diameter of 13.83, and I find it needs a destination diameter of 13.7 to allow for the difference in the center height and the thermal expansion. But once it's settled, it's stable and consistent, and I'm machining parts to within 1/100 of a millimeter. It's really good. You just got to understand what can go wrong and work within those boundaries. Yes, I was really starting to think that the accuracy potential of RapidTurn was fundamentally flawed, and that I should have bought a Slant Pro, because the tool's coming down from the top and the thermal expansion is just too big a problem to deal with. RapidTurn comes, Slant Pro comes in from the side relative to the headstock, so you know that is in theory a much better design. But this has relieved my concerns. I can see that with the control of the RPM and the cycle time and the periods of time that it's not running, you can work within those boundaries. You can still do relatively accurate work. I wouldn't like to try and do extremely accurate work to within 1/10 of a thou, or less than 1/200th. I think you'd be pushing it then. But you know, medium work, it seems quite capable. So whatever that surface finish issue is, it looks like it's going to come and go according to the particular type of machining operation and part geometry. So if you strike it with your RapidTurn, please post a comment to the YouTube video. I'll be interested to see how much of a problem it is overall. Just to give you a graphic example, 50 parts ago I had dialed it in at the diameter at 13.83, and now the parts are coming off. Gosh, that's accurate. 13.83, 13.832. I know I'm only working with acetal and it's very temperature dependent, but you know, we're looking at better than 1/200th on this run, so that's brilliant. Well, that must wrap it up now. I know it all sounded a bit grim at times, but a lot of the process in the recent videos has been learning what are the limiting factors of RapidTurn. As any machine has limiting factors, but learning specifically what are the limiting factors of RapidTurn and where are the boundaries of those limiting factors, and how to work within them to get the best out of it. Thanks for watching, guys. Cheers.